Okay, so then let's start right on time. Welcome being back with me. Our second lecture this week about around Sobolev inequalities. And I want to remind you a bit what we did last time. So the question was essentially, if we have some size information on the gradient of a function, can we then get some improved regularity properties or higher integrability properties for the function itself? And so for us, mainly getting this higher integrability was the interesting point in the last lecture. And so there we worked on the full space Rn and used this Riesz potential to upgrade this information on the gradient of u to u. And today we want to leave this this constellation on the Euclidean space and also get some more inequalities of more local type. And these are the Sobolev-Poincare inequalities that we want to discuss today. And I will jump a bit around in the lecture notes. So we will not start with the first point that you would see in the lecture notes, but instead start with definition 10.13. Yeah, so this is somehow we will introduce some geometric concepts that we will need to specify in which domain constellations we might get such results. So what do we have here? We have omega is some subset of Rn, and we say that it is star-shaped. Star-shaped you maybe know from, I don't know, your complex analysis class or something like this. There we usually discuss star shape with respect to one point. Here we don't want star shape with respect to one point, but with respect to some anchor set. So star shaped with respect to a set E is a subset of omega. And we also want that it's non-empty. Yeah, okay, if it were empty, then this statement would be a bit void. And when is this the case? So this is the case if I take some point y in E, and I take some x from omega, and then I want to have that this implies that the line segment connecting x with y, which I will denote like this, x, y bar, is also contained in omega. Let's make this a bit more concrete with some examples. So we have example 10.14. The first example is a really easy one. So if omega is a convex and non-empty set, yeah, if it's convex and non-empty, then we can of course take any subset E. Convex non-empty is star-shaped with respect to any E in omega. Yeah, of course, in the convex set I can connect any 2 points by line segment that stays in omega. So then I can in particular do it for the points in E. Second example, which is maybe a bit more interesting. Specific example is a Pac-Man. So what is a Pac-Man? Let's maybe draw a little sketch. So this is a Pac-Man, or should rather say it's a hungry Pac-Man. So its mouth is really open. So if the mouth is closed, then it would not work. But with open mouth, it's okay. So let's see, how can it be star-shaped? Yeah, well, let's draw here some auxiliary lines. So we see that here somehow, in this upper half circle, we have a convex set. In this lower half circle, we also have a convex set. So we can place any set E in between this piece of cake here. So maybe I can take some ball like this, and then the Pac-Man will be star-shaped with respect to this set. Okay, so this is E, and then Pac-Man star-shaped with respect to this E. Okay, and of course we notice that this Pac-Man, it's not convex, but it's star-shaped with respect to balls in this special area. So it's really a generalization of convex sets. Okay, so now that we have the notion of a star-shaped set, I want to write down somehow the main result of this lecture, but we'll only prove it much later. Maybe I write it here so that we can keep it. Theorem 10.17. That's the Poincare-Sobolev inequality. So the inequality that gives this lecture its title. Poincare-Sobolev inequality. Okay, what do we have there? We work with any positive dimension, so we have no restriction like we had last time sometimes. We said, okay, we need to be maybe larger than 3 or larger than 2. Then we take some omega in Rn, and we want it to be non-empty. Okay, this is maybe not so interesting. If it's empty, then yeah, all inequalities would somehow be trivial anyway. We want that it's open. Also quite clear if we want to work on Sobolev spaces. We need it to be bounded. So here you might maybe ask, okay, somehow in the past when we discussed Poincare type inequalities, we sometimes said, yeah, okay, maybe finite measures, okay, but here we really need bounded and not just to have a finite measure. And the last point is that it's star-shaped with respect to E and omega, and we need 2 additional properties for E. The first one, also simple compatibility condition, is that it's measurable. And the second one that we need is that it has a strictly positive measure. Yeah, so somehow we want to use this E to do some averaging operations. And when you want to take an average, you need, of course, to have positive measure. Okay, so this is the setting. And then we claim that there is this Sobolev-Poincare inequality. How does it read? It reads, there exists a constant C, which is again depending on dimension. And also, as we had last time for the Sobolev inequalities, it will depend on some integrability parameter Q. So right now there is no Q yet. I will write down the inequality, and afterwards we will have, as last time, some quantification or cases which Qs we can treat. Okay, so there is this constant C, and then we claim that we have the inequality U. It's an inequality in LQ of omega. Yeah, so these were quantities that we want to estimate in the normal Sobolev inequalities. Here we will need to do a little modification, namely we will subtract the mean value of U over E. Okay, and so if we subtract this mean value, then we will get an estimate against the expression as we have here this constant. Then we will have some factors that depend on omega and E, and these are the diameter of omega to n. So here you also see you really need to have an inequality that does not say that something is smaller than infinity. You need a diameter is finite, and this is why you need a bounded set omega. We divide this by n and the measure of E. So also here you see this was the positive measure. And then you need this, for instance, here that you don't divide by 0. Then we get a factor with the measure of omega, and it has as exponent 1 over q minus 1 over 2 minus 1 over n. And then finally we get gradient information Namely, we take the L2 norm of the gradient of u over omega. Okay, so this is the estimate. We require it for u in h1 of omega. And now I should clarify what this q is. So what is q? We have again different cases. So the first case is that n is at least 3. So this was last time this supercritical case. There we can treat q's, they start from 1 and go up to including 2 upper star. So remember 2 upper star, this was this Sobolev conjugate. Sobolev conjugate of 2. Then we have this critical case, n is equal to 2. There we treat q's that go up to infinity but exclude infinity. Okay, and last but not least, we have n is equal to 1. And there we can treat the full range of q, so including 1 and including infinity. Okay, so this is the main result for today's lecture. And we can, as last time, so last time when we showed this Hardy-Littlewood-Sobolev inequality, then we wrote down many corollaries afterwards. This time it will be a bit less, but nevertheless, somehow we want to harvest a bit what we get from this result. So the first one is actually more an example and not a corollary. So example in the sense that I show you what you might take as omega and SE and how the inequality reads then. So as omega, we take some ball BXR, and SE, we take a subset of omega which has a measure that is lower bounded by the measure of omega. So I want to have that the measure of E is at least, okay, here I write first the measure of BXR. So this can of course not be if E is not exactly BXR. That's why I introduce a number gamma here. This gamma is between 0 and 1. And then this is possible. And you can, for instance, you could have in mind some balls inside this ball that have a comparable but smaller radius, or other constellations. Okay, so if we have this, what happens then? This part I can just copy. U minus the average value of U in LQ norm of BXR is then estimated by a constant. Now we have to calculate all these quantities here, but we are somehow lucky because we can, in fact, we can reduce everything to the radius of this ball, yeah, because this, I mean, the volume of the ball, of course, has a linear connection between radius and some dimensional constant. The diameter is just the double radius. For this, we have this lower bound, so we can also express it in terms of the volume of the ball. So in the end, what we get out is constant times r to the power 1 plus n, and then we have 1 over q minus 1 over 2 times the L2 norm of the gradient over the ball. Yeah. So this you will just get out if you did what I indicated here. So yeah, just calculate a bit around with these factors and then it will come out. It's a little exercise for you. So this is the first application. This is an example. And then, so this is 10.18. And afterwards we really have a corollary. This is 10.19. So we work in the setting of the theorem. Yeah, so with setting I mean we take some omega and some e is quantified in this theorem, and also the n's and the q's we take subject to these constraints here. And what do we then get? We get an estimate of u in the LQ of omega norm. So this already looks quite similar to the Sobolev inequalities that we had last time. So somehow this averaging operation here disappeared. Then I get an estimate against the gradient of u in L2 omega norm. So if you have in mind here that, let's say, q were just this 2 upper star, then this would just be the inequality that we derived last time. Yeah, and because we don't derive the last inequality as last time, there's probably something missing. And indeed there's something missing, namely some error term that comes from this averaging operation, and this gives an additional L1 norm of u over e. Yeah. So somehow you can read it a bit as if you also control information on u on this auxiliary set e, then you also get a Sobolev embedding like you got on in the Rn case last time. Okay, and this of course for all u in H1 of omega. Okay. Maybe we indicate a bit the proof of this corollary. So how does it work? Yeah, well, I want to control u, but I only know how to control this quantity. So let's create this quantity here. I just write u is equal to u minus the average of u over e, this first term. Then this I have to add, of course, again. And I apply the IQ norm of omega to this decomposition. When I apply it to this term, then I just use the theorem here. It will, so these factors here I can somehow all collapse a bit, so they are in this implicit constant here. So this depends on omega and e. So this all disappears in the implicit constant, and then just remain with this gradient term here that I have. So this part here, I want to use my colors more this time. This is fine. What happens with the second part? Yeah, well, for this you can just use some trivial inequalities, you could say. So you can say that the average in LQ of omega is just controlled by the measure of omega to the 1 over q over e, and you get u in the L1 of omega norm. Yeah, so this either you know this inequality or you just write down what this expression means here. So in fact you integrate a constant, the IQ norm, then you use maybe Jensen's inequality, or you do some Holder applications, whatever you like, and then you will rapidly find this bound here. Okay, so this concludes this proof. So now we should work towards proving our main result, the Poincare-Sobolev inequality. And so it's not a coincidence that we dealt with the Riesz potential and the usual Sobolev inequalities last week, and today we we work with these similar situations on domains. So the strategies of proof, they are actually quite similar. So we also want to derive a representation that we had last time where we could express U pointwise by some kernel operator that has some mapping properties, then afterwards deduce the inequalities that we are interested in by estimates of this kernel operator. In fact, we want to derive or get our estimate again from some version of the Rees potential. The point is just, so what's the substitute for this potential representation that we had last time? So last time, maybe I make a short reminder. So last time in the beginning we said we have this U in CC infinity of Rn, and then we said that we can write U of x as, how was it, 1 over sigma n minus 1, then we had this integral Rn, and we had here gradient U of y, gradient U of y, and then the inner product with x minus y over x minus y to the n minus to the n dy for all x in Rn. Yeah, so we derived this representation, then we said, okay, we apply absolute values, we somehow transfer this right hand side to the Rees potential, and then we deduce our estimates. But when you remember a bit how we derived this representation here, that we had some arguments. So we said, okay, so we fix some direction, we integrate in this direction, and then we'll run out of the support of C, and then some final value will just vanish. So this is why I only have U of x here and not U of x minus some endpoint. Yeah, this was somehow a bit the argument that we had last time. And now this time when we also want to derive such representations, but we can only work on a domain and we don't have any boundary values that we can use to cancel out this terminal value, then we have to find some substitute to do similar calculations that we had here, but only using the geometric information or the information of the function that we have. And so this will happen in 2 steps. So first of all, we will show a density result by some functions that are in some sense smooth or that are smooth, so that we can even, or at least justify doing some representations here by the fundamental theorem of calculus. Then afterwards we will have a look on what we do about not having a final value that vanishes. Okay, so far as motivation for the rest of this lecture. So this brings us to the next theorem. So this next theorem will be this dense subclass of smooth functions that we can use in a general H1 space on omega. This is theorem 10.12. So I said I somehow jump a bit around in lecture notes with the numbers. So this is in fact the first number that appears in your lecture notes for today's session. This is a result of Myers and Sarin. Okay, what does it tell? We take some omega in Rn. We want it to be open and non-empty. Okay, I said we derive some density result for Sobolev spaces, so somehow these 2 requirements are not actually requirements. I mean, they are necessary to write down H1 of omega. Then we also fix some natural number k, so this is just the order of the Sobolev space. And then what I claim is that this implies that, so what I actually want to write is something like C infinity of omega in H1 omega dense. This I can certainly not write down because this set might not even be a subset of H1 omega. Yeah, for instance, you could have here some functions that are perfectly smooth, but maybe omega is an unbounded set and we have smooth functions that don't decay or might even grow or something like that. So we have to intersect it with H1 omega, but then really get the density result. And it's quite, I mean, it's quite surprising, this result, because we really, I mean, we have no geometric conditions. I mean, open on empty, we needed to make sense of H1, but that's all. There's not really a geometric quality that we throw in the ring. And how can we show this? The proof. And the idea is a bit, so when you remember when we worked with the Sobolev space on Rn, then what did we do there? We said, okay, we use maybe some cutoffs, some modification, and like this we get smooth functions, and the modification will somehow yield an approximation. In a general H1 omega space, we cannot do such cutoff arguments because it would introduce these boundary values, and we somehow learned that an H1 Nord space is not the same as an H1 space. So there's also some intrusive exercise on why in dimension 2, if you take R2 and remove one point, why for instance on this set the space H1 is not the same as the space H1 0. So somehow just taking some cutoffs and then smoothing will not work. But what we can do is we can take many cutoffs very close to the boundary and make the approximation better and better, and then it will work. So it's not a stupid one-time cutoff smoothing procedure, but we will do really many localizing steps. Okay, let's make this precise. We want to take omega and write it as a union of sets J1 to infinity Vj, where these Vj's, they have some properties. So first of all, Vj shall be compactly supported in omega. Vj is open. And we want to have that if k in omega is compact, then this should imply that only finitely many Vj intersect k. Okay. How might we construct such a family of Vj's? Let's do some little drawing, maybe here. So this is our set omega, and so you learned in other lectures that if you have a sector in your lecture and you want to make money, then you can sell it and do some advertisement in your sector. And what I'm going to explain you now is, if you have an open set, not a sector, then you can also sell some advertisement in it. So we can take the same advertisement as last time. So we take the website of the blog of your main lecturer's cycling team. And maybe you should take a look on it, because I heard some rumors that the material presented there is also relevant for examination, but yeah, it's just rumors. So we have our open set. What we want to do is we want to use some form of annually. So we have some inner annually. And then let's take again my colors. So I want to take some first annulus around it. Then I want to take a smaller annulus around it. Yeah, so it's not very nice, but so the green part is somehow also an annulus. It overlaps with the yellow part, and it's smaller than the pink part. And you do this, you're like getting smaller and smaller and smaller. So in the end, you really have shells like this, and then like this, and then like this. And like this, you approach the boundary. And these you want to take as your Vj sets. And if you want to know a bit more about the details, so the details of this construction, they are written out in the lecture notes. But this is somehow an indication how you could do it. You approach the boundary and cut off closer and closer to the boundary. And so then we have the Vj sets. And we also need, for localization argument, we need the partition of unity. So let's take eta j is the partition of unity, subordinate to Vj. Vj. So what does this mean? We have that each eta j is a smooth and compactly supported function on Vj. We have that they have all ranges between 0 and 1. And we want to have that that the sum over j of eta j is equal to 1 in omega. Yeah, so this sum makes sense because we have these overlap properties of Vj, but they also should sum up to 1 in any point. Okay, and what we can do now is, so first of all, we use some lemma from lecture 3, namely lemma 3.9, and some form of product rule. This tells us that eta j multiplied with u is an hk function on omega. Yeah, okay, so maybe I should. So I somehow forgot to write that we should take u from hk omega. So we want to show a density result. So we take some arbitrary element and we want to approximate it in the hk topology. And then by product rule, so this is hk, this is smooth, and then we get it also for the product by this lemma 3.9. And then we need the modifier family. So for this we pick some theta, which is a compactly supported smooth function in Rn. And with this theta, remember, we associated this multiplier family theta t for some positive t. So and then we had that if we take convolution with this theta t and send t to infinity, it will behave as an approximation of unity and approximate u in the R2 topology. And what we can do now is, so we take this function, it's some hk function with a compact support, so we can extend it by 0, and then we are on Rn situation, and there we can modify. Okay, so we consider eta j u modified with theta theta, and I claim that this is a CC infinity function on Vj. Why is this the case? Yeah, well, I have maybe if this is my Vj, then I have the support of my function eta j u in there, and then the convolution with the modifier it will give some extension of the support, but it's somehow controlled by the support of this modifier. So if I make the modifier of this theta t small enough, I maybe get an extension by the support like this. So and if I make this extension of the support here so small enough that it's less than the distance between this old support and the boundary of my set Vj, I will still have my support within Vj. Yeah, okay, but so how I have to take this is somehow really Vj dependent. So I should write here for Tj that is small enough depending on Vj and the support of eta Ju. Okay. Then we take some epsilon positive. That's somehow the error in which we want to measure approximation the HK topology. And so how does the estimate work? We write eta Ju modified with theta Tj minus eta Ju in HK omega topology. First of all, I can throw the derivatives of the HK on the convolution. So this will give me a sum alpha at most k. And I have here d alpha eta Ju modified with theta Tj minus d alpha eta Ju all in L2 omega norm. And then if I take this, so here I took Tj small enough that the support property is good. If I make Tj maybe even smaller, I can make all these approximations in L2 small. Yeah, so you see here, this and this is the same function. They get modified. I make the modifier good enough. And then I get a bound less than 2 to the minus j epsilon. Okay. And now the candidate for our approximate solution is we take u epsilon is just the sum over these j's, eta Ju modified with theta Tj. Okay, why does it work? It's just calculate the difference in the HK norm. So here we have u epsilon minus u in HK omega norm. We can use the partition of unity also for the u. So this will give me a norm j equal to 1 to infinity, eta Ju modified with theta Tj. And on this u I also use the sum over eta j, and that is 1 by partition of unity. So I can write here minus eta Ju, okay, HK omega. Then I use this estimate here, gives me that this whole expression is less than 2 to the minus j epsilon. And I just calculate this geometric sum, gives me epsilon. So I found a smooth function in HK, and its difference to u in the HK norm is less than epsilon. Epsilon was arbitrary. So this shows density. Okay, so we have to make some space on the blackboard. Okay, so far about the density result that we will need for to derive a potential representation for u. Now we come to the actual potential representation, and this is lemma 10.15. What does it say? Here we work in dimension at least 2. We take as before omega in Rn, and it's open, bounded, star shape with respect to some set E. E of positive measure. And yeah, exactly. And we take u in h1 of omega. And then I claim that we have the following representation. We have that, so I don't claim directly representation, but directly the pointwise bound. So I say that ux minus the average of u over e, an absolute value, can be bounded by the diameter of omega to the n over n times the measure of e. And I take here an integral over omega. Then here gradient of u y over x minus y to the n minus 1 dy. This is for almost every x in omega. Okay, and so here you can already see that there's somehow relation with the Rees potential that we discussed last time. Yeah, so let's do the proof, or at least start with the proof. So it goes in two steps. Maybe it's also not so surprising for you, given our strategy from the last lecture. So in the last lecture, we first showed it for some more regular functions from a dense subclass, and then we somehow extended it to the full Sobolev space, and here we'll directly do it in this one lever, but somehow the two steps of the proof correspond to these two stages that were in the last lecture separate results. Okay, so the first step is we start with u, which is a smooth function in omega. So somehow this is the case that comes out from the Meyer-Serrin class. What happens there? We take some x in omega. We take y from e. And then you remember last time we always had this unit vector there. And this time we directly start with a specific unit vector. Namely, we take some omega xy, which is defined as y minus x, and then normalization. Okay, and when we have this, then so last time we said we have u of x, and we wanted to write it as some integral from 0 to, here we had infinity last time, and then we took inside the integral dt over u of x plus t, and here was this unit vector, so here I directly take this omega xy dt. And here we had also some minus. Yes, and there we said that last time we took here as the endpoint infinity, then we said, okay, we make it so large that this point here will somehow lie outside the support, and then it's 0, so we just get the slower endpoint from the one-dimensional fundamental theorem of calculus integral and no endpoint. So here we don't have this vanishing endpoint, so instead I will write here an integral over x minus y, and when you evaluate this at the endpoint, you will just recover here u of y. Okay, so this is somehow a bit the difference and where it comes from. Then we can again compute this by the chain rule, and then get minus the integral of 0 to x minus y, gradient of u evaluated in x plus t omega xy, and then an inner product with omega xy dt. Okay. And then last time we said we averaged something, or we averaged the full expression, and then we didn't get any change on the left hand side because it was independent of the variable over which I averaged. This time I don't average, but I integrate over some set. I integrate over the set E. But this will change the left hand side. So if I integrate over this left hand side, I get here the measure of So maybe let's write it. Integrate over E. For this guy, I get the measure of E times 3x, because this is really just a constant. But for this, I would normally get an integral over E uy dy, but I will put it into some. So here I would normally get this, but I will write it in some different shape. So I will also do some averaging operation here. To compensate for this, I have to multiply by the measure of E. So I just make some large brackets here. This is the left-hand side. Then I will get that. So did I write it here? Yeah, okay, let's first write it like this. So then I get. I don't write the integral over E here, but I write integral over Rn. And then put some indicator function in the integral. Indicator of E, y, and then the rest I copy. 0 to x minus y. Gradient of u, x plus t omega xy dot omega xy dt dy. And in the end, I said I want to get not a representation, but a bound. So I can apply, I write it here. Yeah. So the brackets I will remove by absolute values. I apply absolute values to the other side. Eliminates this minus. I make some less or equal, and I can pull it inside the integral by a triangle inequality. So I will also get here some absolute values. Yeah, so the absolute value will kill this because it's a unit vector. Okay, so and this is the expression that I want to further manipulate. So what do I do here? I want to use polar coordinates for Rn, of course. So I will write this y as x plus r nu. So I will do some translation, and then I will write polar coordinates with this as unit vector and this as radius. This will give me integral 0 to infinity, integral over this sphere, b0, 1. 0 to r, so this is of course then just this r here. I get this indicator function e, now evaluated in x plus r nu. Then here the gradient of u evaluated in x plus t nu. Okay. Then I get here from using the polar coordinates, I get an r to the n minus 1. Then I have dt, I have the sigma of nu, and I have dr. And so next I want to use a Fubini. I want to use a Fubini to switch these two guys here. Also switch here. Okay, what happens then? I get integral from 0 to infinity, integral over the sphere. When I use Fubini, from the 0 to r will become t to infinity. Then I have here Rn to the minus 1. I have this indicator function, x plus r nu dr. Yes, so I want to have this as an independent factor, and afterwards I copy what's left. So this absolute values gradient of u evaluated in x plus t nu dr d sigma of nu dt. Okay. So now some observations with this indicator function. So first of all, if I take this r larger than the diameter of omega, then this will certainly be a point that lies outside of omega, and then in particular outside of E. So I can replace this integration to infinity by the diameter of omega. And then the second observation is, so you have if this is my omega, and then here I have E, and so here this is x. Okay, this is x. And then I have some straight line in nu direction. If I follow it for the length r, I will end up in E. This is somehow what having that this indicator function evaluates to 1 says. That x, I go in direction nu for length r, I end up in this set E. But now that I'm star shaped with respect to E, it tells me that this full connecting line segment, so the line or all x plus t nu, where t is between 0 and r, this is also contained in omega. This is star shaped. Element omega by star shaped. Okay, so I can introduce here some additional indicator function, namely that the point what I wrote here, x plus t nu, is an omega. So this is one implies that this is one, so I can just add it. And if I write down what I got by these manipulations, and I use the additional transformation that this is y, so somehow I switch polar coordinates. Like this, I could introduce this, and I could introduce this, and then I switch back to Euclidean coordinates, and then it will give me here an integral over omega. So this is omega, not Rn, due to this indicator function. This I copy, gives me gradient of u in y. Okay, this is good. Then I will get some x minus y to the n minus 1. So this comes from using polar coordinates. So this is just r from the polar coordinates. And this integral I have to calculate. But it's easy to calculate. Yeah, I can in particular integrate from 0 to diameter of omega. I know what the antiderivative of this function is. So this will just give me diameter of omega to the n over n. Okay, this is almost what I claimed here, except that this normalization by measure of E is missing. But this is okay because I had here a measure of E on left hand side. So if I divide by measure of E, gives the claim. Okay, so this was the first step. Now we can do a bit short break, and then I present the second short step. Okay, so then I suggest that we continue. Second step of the proof. Luckily, the second one is much shorter than the first one. So I want to do an extension by density. Yes, and this is essentially, we know this argument from last lecture. So there we had, or it's as in Corollary 10.18. How did it work there? We said that we have some identity that holds on a dense subclass, and okay, the left hand side is somehow good. And the right hand side defines a bounded operator, but it's a priori bounded on the full space. It's not some extension by continuity. So we can just say, okay, we argue as in here, we replace our density result and use now my Theorem. And the second modification is that the argument last time was that the right-hand side is directly bounded by the Rees potential. And to see boundedness, this time it's almost directly bounded by the Rees potential. But, but use my Theorem as density result. And right-hand side bounded by J, and then we take the indicator function of omega and then apply the argument, but of course this then still a mapping with the same properties as the Rees potential. So this somehow gives that we can do the same argument as for this Corollary 10.8 in dimensions at least 3. So good for n larger than 3. So this is, I think it's also discussed in remark 10.16. And then we also have the dimension n equal to 1, at n equal to 2. Yeah, so where was it? Here I said n is at least 2 to treat this case here. How does it work? Well, I use that omega as a bounded set. So we can say that LP embeds into LQ, all of omega, of course. Where Q is strictly less than 2, and then we can do this argument with the Hardy-Littlewood Sobolev maximal inequality with 2 replaced by this Q, and then this Q will have an upper Sobolev conjugate that's finite. Okay, so we use this embedding and then Hardy-Littlewood Sobolev. With Q is okay, since Q upper star is finite. So there we use also boundedness of omega. Okay, and then this completes the proof of the Poincaré-Sobolev inequality. Sorry. So this concludes the proof of this preparatory lemma for the Poincaré-Sobolev inequality. And now we want to deduce theorem 10.17 from the lemma, but it's fairly simple. Yeah. So the theorem is written up there for a reminder of you. So we start with two reductions that will make our life easier. So first of all, I already said there we have some range of admissible Qs and should hold for all Qs in this range. But what I claim here is it suffices to show it for one such, or if I have it for one such Q. So result for Q naught implies result for Q in the interval from 0 to Q naught. So in this sense, often it's sufficient to treat one extreme case and then conclude the rest from it. How does it work? This is by Hölder's inequality. So by Hölder's inequality. So we will see this argument for one of the cases also. So I won't give more details on it right now. And the second reduction is right there. It's not really a reduction, but an observation. So I mean, we do the same as what we always did. We somehow derive a pointwise bound using the Riesz potential. So I can write that u of x minus the average of u over e is bounded by diameter of omega to the n over n times the volume of E, and then I get here the Riesz potential now applied to indicator function of omega, and then absolute value of the gradient of u, and this Riesz potential is evaluated in x. Exactly. So this we just get from combining the previous lemma with the definition of the Riesz potential, and then somehow we can follow the same scheme here, that we use mapping properties of the Riesz potential to deduce the inequalities that we are interested in. Okay, so with these reductions, let's start with the first case. Supercritical case. What do we do there? Well, there we can take as Q naught, we take 2 upper star, and this is good because 2 upper star is the critical case of the range in which we claim this result. So if I show it for this Q naught, then I show the full result in virtue of this first reduction. And what happens then? Yeah, well, it's almost trivial. So I apply the Q naught norm of this, but this is exactly the statement of the mapping properties of the Riesz potential. They get on the right hand side. So if I apply the 2 upper star norm on this, mapping properties of the Riesz potential give me the L2 norm of this, and this is precisely the claim of the theorem. Okay, so this is immediate, since J is L2 to L2 upper star bounded. Yeah, and what we maybe should see is that, so this constant is then also fine, but it's by definition of the upper Sobolev conjugate, okay? This is the first case. Second case is the critical case. What happens here? So here we take as Q naught some number that is larger than 2. So remember, the the statement was that we can show it for all q of arbitrary size, but not equal to infinity. So of course I can take here this q naught larger and larger and larger over 2. So this will somehow give me all, the upper range of the statement, and then the numbers less than or 2 and less than 2 will follow by the first reduction. Okay, so what do we do then here? If q naught is strictly larger than 2, then I can define, so last time we had the Sobolev conjugate, which is sometimes also called the upper Sobolev conjugate, and now we define a lower Sobolev conjugate. So we define the number q naught lower star as 2q over 2 plus q. If you like to think in 1 over notation, then we had last time that this 1 over q upper star was 1 over q minus 1 over n, and then this lower star thing is defined by 1 over q lower star is equal to 1 over q plus 1 over n. And if you see these two relations, then it follows, and what is to be expected, that if I take upper star and lower star, they will just cancel out. So I have that q naught lower star, upper star recovers q naught. And then what I do is I say, okay, indicator function u of the gradient of u. So by assumption, the gradient of u is in LQ naught. But did I write here? No, sorry. What did I write here? Okay. So this q lower star is in particular a number which is smaller than q. So because I said that the gradient of u is in LQ, it's also in LQ lower star. This is by embedding of the LP spaces when omega is finite. So this is in LQ lower star of omega. And I just want to apply my results with q lower star and not with q. Okay, what happens then? I write here u minus the average of u in LQ omega. Then I use this formula from Barfier, namely that this is the upper Sobolev conjugate of q naught lower star. So I can reply my results with q naught lower star. So the like the Hardy-Littlewood Sobolev inequality, for instance, I would apply this with q naught lower star, and then it gives me here a bound against the diameter of omega to the n over n measure of E. And then, okay, so first of all, J, sorry, I was a step too fast. So first we just use that the Rees potential maps q naught lower star to q naught lower star upper star, which is q. So this gives me here gradient of u in LQ lower star omega norm. What did I write here? Okay, and sorry, I'm writing complete rubbish. So first of all, I want to use this bound here. Gives me this, but with the same q. Now I use Hardy-Littlewood Sobolev. With q naught lower star. then I get a bound against diameter of omega n over n measure of E, indicator function of omega, gradient U in LQ naught lower star omega, and the last step I use Hölder. So this is somehow the argument that I indicated here, and then these first constants here I copy, and then I get here an additional omega to the 1 over q lower star minus 1/2, and then gradient of u in L2 of omega. And when you look at this parameter here, so this is just 1 over q because the dimension is 2, and this is just the exponent that we claimed in the theorem. So this completes case n is equal to 2. And then finally n is equal to 1. This is again the easiest case for me because this is exercise 10.2. So there you don't need any deep result, it's just using the fundamental theorem of calculus in a clever way. Okay, then to make some space on the blackboard again. Yeah, so somehow this was the inequality part of today's lecture, and there comes now section 10.3, and 10.3 is supposed to show some other applications of the Meyer-Serrin result. So what else you can, or what you can derive for a general H1 function by this density result. Okay, so 10.3. Further applications of Meyer-Serrin. So here we will, usually the H1 space, you work with complex functions, of course. We will focus a bit on the case of real-valued Sobolev spaces. So only real-valued functions. From now on. And then we want to show the following chain rule for H1. Theorem 10.20. Chain rule for H1. Okay, what do we say? We take omega as before is some open non-empty subset of Rn. Then we take u is an H1 function, and as I said, real-valued. And I take some second function for the chain rule, of course. The second function is a bit more regular, so the second function is some phi. It's a function from R to R. We have that phi is C1. So yeah, what I mean with this is it's smooth, or not smooth, it's differentiable, and phi prime is bounded. And we want to have that it vanishes in 0. And what I claim then is that we have that phi after u is still h1 omega function, and its gradient can be computed. Gradient of phi after u is what you expect, so it's phi prime after u times the gradient of u almost everywhere. Okay, let's see how the proof works. So for convenience, I give this bound for the derivative a name. I say that C is the L infinity norm of phi prime. And then, of course, it follows by the mean value theorem that that phi is the Lipschitz function, and the Lipschitz constant is just this C, or it's at most this C. And but we can say even a bit, or derive a further property, namely because we know that phi of u vanishes in u, we can also gain from Lipschitz something like a linear growth. So this reads as follows. Lipschitz plus phi of u is equal to u implies that, well, how did I write it here? That phi of t is bounded by c times the absolute value of t for all t real. Yeah, so to somehow imagine that you extend this expression by minus phi of 0, and then you use Lipschitz property here, and then you get this linear growth. Linear growth. And now, first of all, we can use this linear growth to get some boundedness properties for quantities involved with this. So we get that phi after u in L2 norm is bounded by c times u in L2 norm of omega. Yeah, okay, just you apply to this pointwise this inequality, and you already have it. And also you get that phi prime after u gradient of u in L2 norm of omega is bounded by c times the gradient of u in L2 omega. Why is this? Yeah, well, phi prime is bound by c, so this is bound by c. You pull it out and you remain with the gradient of u. Okay, let's give these two estimates a name. Let's call it star. Now at some point we should use Meyer-Serrin if it's supposed to be a further application of it. So let's do it. Meyer-Serrin gives that there is a function or a sequence of this class of dense functions. So there is some uj in C infinity of omega intersected with h1 of omega, such that uj converges to u in h1. Okay, this is just Meyer-Serrin. And without loss of generality, we can also say that we have here pointwise almost everywhere convergence by passing to a subsequence. And now, what's even the gain of using this density result? While here we have really, so the UJs, they are smooth functions. My phi is a C1 function, so I can use the classical chain rule for a concatenation of phi with UJ. And then I want to extend it to the limit U. Okay, so phi after UJ satisfies classical chain rule. So then this gives me that the gradient of phi after uj is phi prime after u gradient of u. Now I can, so for first question is this also in H1, but there I can use my star. So this is in H1 by star. Yeah, it's just written here, and so I mean here it's formulated with u, but it's of course an estimate that it holds for all u in H1. So I can also apply it with uj, of course. I missed some j's, and so what I said now is so here we have really this identity that we want to get for u in the end, and we want to pass to the limit. So we should just calculate the difference between what we want to get and what we know what holds in the H1 norm. And if we get a good bound for this, then we can pass to the limit. Okay, moreover, I first want to see that phi uj converges to phi u in L2 norm. Phi after uj minus phi after u in L2 of omega norm. How can I bound this? Well, it's a bit the same argument like here, but we don't use linear growth, but really the full Lipschitz property. Then we can bound this by c times uj minus u in L2 omega. Okay, but this goes to 0 as j to infinity. This was just by choice of the approximate sequence. And then the second term is a gradient of phi after uj minus, here it's already written out, right? Okay. Phi prime after u gradient u L2 omega. So here on this side, this is somehow what should come out, and here So this I could calculate by the classical chain rule here. This I don't know if it comes out if I apply the gradient to phi u, but I wanted it comes out, so this is why I wrote it here. I can bound this by here I plug in this identity, and then I add some zero term to group things nicely. So I write phi prime after uj gradient of uj minus gradient of u L2 omega plus phi prime after uj minus phi prime after u, and this all to the gradient of u Lt omega. So you see really here you have phi prime uj gradient of uj. This is what's written here. Then this part and this part cancel out, and this is what's written here. Now I want to argue that both terms go to 0. So for the first part, This is very easy. This prefect is again bounded by C. And for this part, we can just use that uj is an approximation in H1. So this goes to 0 by H1 approximation. And for the second term, here we have to look a bit closer. So what we want to do is we want to use the dominated convergence theorem. So we can certainly apply it because this is an L2 and this function is bounded, this function is bounded. So if I get pointwise that it goes to 0, I can apply dominated convergence and everything will be good. And why does this converge pointwise to 0? Yeah, well, we know that, so we said that we can assume without loss of generality that uj converges pointwise almost everywhere to u. And if I compose both with the same function phi prime, then of course the composition will also go to 0 pointwise almost everywhere. So yeah, pointwise almost everywhere to 0. I cannot write anymore. 0. And then dominated convergence is good. So yeah, and then the claim follows by just passing to the limit. Okay, so implies claim by passing to the limit. Okay, so this is it for lecture 10. Do you have any questions left? If that's not the case, then thanks for being with me, and then wish you a good Christmas break, and then next year Moritz will be back and give you the lecture.